Okay, let's carry on with some more linear approximation examples. Okay, so this one's a little different. We're given a function on the left side here, f of x, some kind of complicated function, and we're told that it's approximately equal to that. So this side is supposed to be the linear approximation. And we're going to verify that that is in fact the linear approximation at x equals 0. Now this is a key point. Notice that at every different a, so if I chose a different a value, I would have a different tangent line and therefore a different linear approximation. So you always have to say at such and such a point. Okay, then we're going to use it to determine the values of x for which the linear approximation is accurate to within a certain amount. Okay, that sounds like a lot, but we'll figure that out when we get there. Okay, so let's start with this function. And here's our function. What does this graph look like? It's hard to say. Let's not worry about that. What we're going to do is start with letting a equal 0. That's that's where we need the linear approximation. So let's do an easy one first. What is f of a? F of a would be 1 plus 0 to the power of -3, which is 1. What is f prime of x? So now we'll use the power rule. So we bring down the -3, subtract 1, and multiply by the derivative of the inside. What's the derivative of 1 plus x? Well, it'd be 0 plus 1. So it's just -3, 1 plus x to the -4. What else do we need to know? We need to know the derivative at a, which is at 0. 1 plus 0 to the -4. That's just 1, so -3. So whatever this function is, so who knows what it's doing, at 0, we know that maybe I should have drawn this a little more carefully. I'll use this spot. At 0, I know that the slope of the tangent line is -3, so that's not a bad, that's the slope of -3. And I know that the function here, L of x, is f prime of a, x minus a, plus f of a. And now I know all these things, so that's -3 times x minus 0. What is f of a? Plus 1. -3x plus 1. All right, and then look at that. That's what it is, right? -3, that's 1 minus 3x, same thing. So we have found the fly. We have found that L of x is -3x plus 1, which is right. Okay, now this is trickier here. So determine the values of x for which the linear approximation is accurate to within 0.1. So what we're trying to say here is we want the difference between the actual function and the line to be not too big. It has to be less than or equal to 0.1. So I think what would help actually is it would help if we knew whether the line was on top or below, as in an underestimate or an overestimate. So this is where it would be good if we find the second derivative. What is the second derivative of x, of f? So let's go back. Where's the first derivative? There's the first derivative up here. What is the second derivative going to be? So I'll bring down the -4. 1 plus x, and now it's -5, times the derivative of the inside, which is 0 plus 1. So I get 12, 1 plus x to the 5th. So what's the second derivative at a? A is 0. So it's 12, positive. So that means this graph, a better sketch would be that it looks like concave up. And then the tangent line here is going to be beneath it. This is at 0. So what I know is that now the function is always a little bit above. It's always above the tangent line. This is the derivative. This is the tangent line. So what I'm looking for is, where is it that this distance here, when is it that this distance is equal to 0.1? When is this distance equal to 0.1? Because that will define this interval where the approximation is pretty good. So what we're going to do is we're going to find that. We're going to set the function minus the linear approximation equal to 0.1. We're going to solve that. There are going to be two solutions, left and right. Let's see what happens. So what is it? It's 1 plus x to the power of negative 3 minus, what is the linear approximation? It was minus 3x plus 1 equals 0.1. Somehow we have to solve this. Okay, so let's see. Let's write this in a slightly more familiar way. Okay, so this would become plus 3x. This would become minus 1 equals 0.1. And why don't I put everything on the left side? So I'm going to put everything on the left side. So that means I subtract 0.1, so I get negative 1.1. So this equation is actually not easy to solve exactly. So what I'm going to do is use my graphing device, Desmos, and I'm going to just look, when is this function equal to 0? Those will be the solutions. So let's try that. We're going to punch this into Desmos. And this is a perfectly good way to solve an equation, right? Desmos.com. And this is something that you can do, at least while we're in the online period. You can do it anytime yourself, right? On an exam, on a tutorial. Nothing wrong with using a computer to solve equations. Minus 1.1. So what are we doing? We're looking for the places where this equals 0. Now I can't just do that here in Desmos, but I can zoom in and look for the points where it equals 0. And look at that, there are exactly 2 points. So let me, if I select this point, I can actually get an exact answer here. I'm not sure if it's exact or if it's approximate, but that's one of them, negative 0.1162. So we get, one answer is x is negative 0.1162, or what's the other one? The other one is here. Okay, it looks like that's 0.1441. 0.1441. 0.1441. So what we've found is that, let's just connect that back up here. On the interval from negative 0.1162 up to 0.1441, the linear approximation is accurate to within 0.1. To within an error of 0.1. Now, somehow Desmos seems to have found the exact answers. I'm not sure if it did or not. I don't think there's any very accessible way for us to solve that exactly. But in any case, I'm content with these numbers. These are this is normal when we're doing approximation, is um, we don't get closed formulas. We don't get exact formulas. That's the way it is. Okay, so let's move on. Okay, now this is an example that is a bit scary because you're not given very much. It just says use linear approximation to estimate the square root of 100.5. Now, one thing that you shouldn't do is don't just use your calculator to find the answer, right? So square root of 100.5 is 10.02496 something. So don't do that. That's not a linear approximation. That's an exact answer. So you might say, well, why don't I just do that? Why don't I just let the calculator do the work? Well, we're trying to learn a concept, which is to use. Okay, let me draw the picture for it. We're trying to learn the concept. It's the principle that underlies how your calculator does get the answer. How does this thing work, after all? How does it know the square root of 100.5? Deep down, it's actually doing something like what we're doing right now, but it has to do it. So let's see here. What are we doing? We know, think about this. What do we know exactly? We know that the square root of 100, we would know that is exactly 10. So that means that the square root of 100.5 should be 10 plus something, right? It should be just a little different than 10. So this is what we're thinking to ourselves before we start. And so what we're doing is we're dealing with this function. Y is, or let's say f of x is the square root of x. And we're dealing with it near the point a equals 100. And I know that at that point, the y coordinate is 10 exactly. So what we're going to do is we're going to follow the tangent line. We're going to use that, and we're going to follow the tangent line until we get to this point, which is 100.5. And that will be, whatever the y value is there, that'll be close to the true y value, right? You can barely see the gap in between them. So how do we do that? We let f of x equal square root of x. A is 100. So what is to do the linear approximation, remember, we need to know the tangent slope, x minus a, plus f of a. I can't help it. I want to show one more way to look at this. So notice that this form is equivalent to saying that L of x minus f of a, okay, let me see here, need some space, L of x minus f of a divided by x minus a equals f prime of a. So on the top here, L of x minus f of a, that's actually what we would call change in y. On the bottom is change in x. So the okay, I think I'll leave that observation at that point. We'll come back to that when we do differentials. Okay, so what is L of x? What's the derivative? I need to know the derivative at a, so I'll calculate it up here. F prime of x is, this is one we've done a couple times, so I'll just write the answer. What is f prime of a then? It's going to be 1 over 2 square root of 100, which is 1 over 20. So the linear approximation is 1 over 20 x minus 100 plus, what is f of a? 10. Right, so I'm ready to write the answer then. So I know that the square root of 100.5 is approximately, okay, let me write this, which is f of 100.5 is approximately L of 100.5, which is 1/20th 100.5 minus 100 plus 10. Okay, which is what? Mosquitoes here on Quadra. So it's the slope, which is a half, times the change in x, which is 0.5. So that gives me the run, 0.25 plus 10. So it's 10.25. That is my linear approximation. And notice that the, oh, what happened? I lost a 0 on my 20. This was 20 and it became 2 here. Let's correct this slightly, 20. So 20 times a half, or 1/20th of a half, is actually 0.025. There we go, that's better. How did I know there was something wrong? Was because I knew that this should be close to this, which is the exact value. So maybe it was good to do the exact value first. So notice, is it an underestimate or an overestimate? Is this an underestimate or an overestimate? It's an overestimate because, well, you can see that it's too big. It's a little bit bigger than the exact value. And we know it should be an overestimate because this function is concave down. The tangent line is on top. Okay. Now, one more. All right. One more very similar to what we just did. We're given just a little bit of numerical details here, and we have to fill in the whole kind of conceptual background for it. So explain in terms of linear approximations why this approximation is reasonable. Why is this a reasonable approximation? Well, what is this even saying? What is that exactly? 1 divided by 9.98. What it is exactly is 0.10020004, and it goes on. So that's pretty close to that. This, if we dropped the everything after the fourth decimal point, it would be the same. Now, where did this number even come from? It came from linear approximation. So here's what we're doing. We're saying, imagine this function, f of x is 1 over x. That's where this is coming from, right? This is 1 over something. Where do we know the exact value of 1 over x? Not at 9.98, but if we choose a equals 10, then we know the exact value, right? F of a would be 1 over 10, which is 0.1. So we're thinking, like, what can we do without a calculator? Again, after all, how does the calculator work? It's doing something inside that doesn't require a calculator, right? The calculator can't call on another calculator to do the work. It has to do it somehow by itself. Okay, so so that's our kind of, I would call this a base point, right? It's the sort of starting point. Let me write that more clearly. A is the base point, or we could call it maybe a reference point. It's where we start. And then we're going to go a little bit to the left because we're going to put in 9.98. But first thing is we want to find the linear approximation. So what is the derivative of 1 over x? The derivative of 1 over x. Let's write it like this. X to the minus 1 prime is negative 1 times x to the negative 2. So what is the derivative at 10? It's negative 1 times 10 to the negative 2, which is negative 1 over 100, right? So what's the linear approximation? F of x is approximately L of x, which is f prime of a, x minus a, f of a. Okay, so we're ready to put these things in, right? We know there's the slope, and here are the x and y values. So it's negative, oops, the slope is negative 1 over 100, x minus the starting point, plus the starting point y value. So therefore, 1 over 9.98, which is f of 9.98, it should be approximately L of 9.98, which I plug that into the linear approximation, and I'm going to be able to evaluate this without too much difficulty. So what do I get? Minus 1 over 100. 9.98 minus 10, that'll be negative 0.02 plus 0.1. And let's see here, so that becomes plus, and then dividing by 100 is the same as shifting the decimal point 2 more times. So that becomes 0.1002. Right, so what I found was that this is approximately equal to 0.1002. And that's what we were trying to prove. This is exactly what we intended to prove. Sometimes when you write a proof, you can say QED, which is actually Latin for this phrase. It's Latin for which is what we intended to prove. Quod erat demonstrandum. Quad erat. I don't know Latin, but demonstrandum, which was to be proved. All right, so linear approximation again it has some practical importance for us, but when mainly as a theory that underlies calculators and other technology. Probably what's more valuable about linear approximation is that it leads to what we call higher order approximations, not just linear, but parabolic or cubic, fourth power, fifth power, even infinite power. So an infinite degree approximation is called a Taylor polynomial. And it sounds bizarre, but it's actually something that's very important within science and math. Okay, so this is just the first step towards doing Taylor polynomials. And so in the next video, we're going to be looking at differentials, which is very, very closely related to linear approximation. It's practically the same thing. See you then.